Hey everyone, welcome back to Robotics. I hope you guys are doing well. Today we have our 20th lecture on the mass matrix. All right, so let's get started with a video. In this video, you're going to see simulations of a variety of different robots. And the idea is to try to make simulations that are very realistic so that whatever happens in sim is very close to whatever would happen in reality. If I can have such an accurate simulation, then it becomes a really valuable test bed because I can in simulation, try out different controllers and different ways of moving my robot, and then transfer whatever works well there back into reality. So one goal is to try to make these accurate and very high fidelity simulations. But to do that, I need to understand dynamics. I need to understand how the forces and torques I apply with these robots will cause the robots to move around and interact with the world. And so that's what we're going to be talking about in today's lecture, how we can derive the dynamics for a serial robot arm. Specifically, I want to talk about the first part of that, which is the mass matrix. All right, so let's pick up where we left off in our previous lecture, where we were talking about the dynamics for these serial robot arms. And we reached this equation. Now it's got the joint torques tau, the joint position theta, with velocity theta dot and acceleration theta double dot. We understood those terms pretty well, but the terms that are new and we need to figure out are this mass matrix, the Coriolis matrix, and the gravity vector. So in today's lecture, I want to focus on the first one, this mass matrix. All right, and here's the equation that we're going to need to find the mass matrix. And it's a complicated equation, so we're going to talk about it in parts. So first off, what is the mass matrix? Again, the mass matrix is a symmetric and positive definite matrix. It's going to be n by n. So if your robot has, for example, 4 different joints, your mass matrix would be a 4 by 4 matrix. And the way we build it is we look at the mass matrix for each of the individual links, and then we're going to add those together. So that's why we have this summation from I equals 1 to n. We're going to start off with our first link, and then we're going to go up to our nth link. So I is like the current link that we're looking at. Okay, now let's look at some of these terms on the right. There are a couple that are pretty straightforward, and that includes the just mass. So mi, that's going to be the mass of the ith link. So if I'm looking at link 1, m1 would just be the mass of that link. And that's a scalar, just a 1 by 1. The other term that's a little bit easy is this inertia matrix I subscript I. So this will be a 3 by 3 matrix telling me about the inertia for the x, y, and z axes. So for this course, you can assume that the link mass and the link inertias are just given to you, or you can derive them from your robot's design files. Using something like CAD, you can see what these values are. The terms that we want to focus on include the Jacobian and the rotation matrix. So Ji, that's going to be the Jacobian for the ith center of mass. And Ri, that's going to be a rotation matrix from the forward kinematics to the ith center of mass. So a couple things have kind of changed here. You know, in the past, when we were thinking about Jacobians or forward kinematics, we usually were thinking about that for the end effector, trying to find one Jacobian for my end effector and one forward kinematics for the end effector. But now, because I have to think about how each of these individual links is moving, I'm going to need to find the Jacobian for each link. So I want to find the Jacobian for the first link, the Jacobian for the second link, and so on. The same is true for my forward kinematics. And even a bit more specifically, I want to find the Jacobian for a specific point on that link called the center of mass. So for each link, I'll look for the center of mass of that link, and I'll find the Jacobian and the forward kinematics to that point. So you might be wondering, how do you do this? It's actually pretty straightforward if you can build on what we've already covered in this course. So a little bit of recap. So forward kinematics and Jacobian, if you want to find them for the ith center of mass, there's really just 2 things you need to do. First, just identify where is that center of mass for that link. Let's say it's the first link. All right, where's my first center of mass? Put a coordinate frame there. Call that, let's say, A. And then set your initial transformation matrix, T of 0, set that equal to the transformation matrix from S to that A. So that'll be T, S, A, 0. So that's going to be your home transformation matrix. And it's just a transformation matrix from S to wherever that center of mass is. Then for your screws, find your screws normally up to the center of mass. And then after that center of mass, set all your screws equal to 0. And the idea there is the velocity of these different joints that come after your center of mass won't have any impact on your forward kinematics or your Jacobian to that center of mass. So again, set your screws after that center of mass just equal to 0. If you do these 2 steps, you're all set. You can just call your forward kinematics and your Jacobian function, and you'll get out the correct values for your forward kinematics and Jacobian. Of course, you're going to have to repeat this process once for each different link. So again, if you have 3 different links, you'll have to go through this process 3 times of finding the forward kinematics and finding the Jacobian. I want to have one additional note about that Jacobian. So if you look at this equation, I don't just need the Jacobian, I need JV and J omega. And so you might be wondering, oh, what are these? What is JV? What is J omega? We've actually seen it before. It's the angular components of my Jacobian and the linear components of my Jacobian. So the Jacobian is a 6 by n matrix. The top 3 rows correspond to the angular velocity. The bottom 3 rows correspond to the linear velocity. So you just take your Jacobian and separate out by rows. Top 3 are J omega, bottom 3 are JV, and there you go. All right, so that's all the terms you need, but I think an example is necessary to understand how you apply them. So let's go through an example of finding the mass matrix. I want to focus on this robot over here. Now this robot, it's got 2 links, right? I've got my prismatic joint at the base, I've got a link, I've got my revolute joint, I've got another link, and then here's my end effector. I've got my spatial frame, and this is kind of attached to the ground right here. And then let's see, I've got these 2 different links. And previously we just had things like theta 1, theta 2, and like the link length L here. Now I've got these other things, I and M. Well, that's the inertia matrix and the mass of each of these different links. And in the problem, I say that the centers of mass are going to be at the ends of each link. So my first center of mass will be right here at kind of the base of my second joint, and my second center of mass will be right here at the end effector. Also, I've given to you the definition for the second inertia matrix, I2. It's going to be all zeros with, on the bottom right, some sort of inertia around the z-axis. And that's because if you think about this joint, when you rotate the joint right here, this link is just rotating around the z-axis, so it only has inertia around that z-axis. All right, so this is our problem setting. Now let's try to find the mass matrix. So here's the equation, and I've just spelled out the equation from before, but for a robot with 2 links. So I goes from 1 to 2. So here are my 2 different terms. Now maybe pause the video, think for a second. Given the way that this robot is moving, are there any of these terms that are going to drop out and maybe we could remove from this equation? Maybe you recognize that this first joint, it's a prismatic joint, and that means that this link is only ever going to extend and retract. It's never going to rotate. And so there isn't any sort of angular velocity component for that link. And that means this term right here that captures the contribution from this angular velocity is going to be 0. And so I'm left with just this for finding my mass matrix. But it's still not quite that easy, right? Because I have to figure out what is each of these Jacobians, what are these rotation matrices. I still need to find each of these different terms. So let's go through that process. All right. Let's look at our first center of mass. And we know that that first center of mass is at this point right here. It's at the end of the link. And I just picked the end of the link for the purposes of this lecture. In general, the centers of mass could be at the center of the link or maybe even more towards the base. But for this lecture, let's just say it's at the end of the link. I'm going to need to find my home transformation matrix. I'll get the screws normally up to that center of mass, and then I'll set the screws after that center of mass equal to 0. So when the robot's in its home position, this joint is actually right on top of the spatial frame, right? Because this length right here, that's theta 1. At the home position, theta 1 will be equal to 0. And so my initial transformation matrix is just identity, right? So for this specific center of mass, I've got identity as my home transformation matrix. My screws, I have 1 screw that's normal, and that's the screw for this prismatic joint, which is just extending off to the right. So I've got 1, 0, 0 for the pointing off to the right, aligned with the x-axis. And then my second screw is going to be all zeros because, again, I'm looking at this first center of mass, so I don't need to worry about any screws that come after that center of mass. So here are the main things I need to find. And once I have these, I can use the code that we've already built to find the Jacobian and the forward kinematics to this center of mass. So let me walk you through the code. Here I'm declaring L as a real variable. I'm not going to be actually using it yet. I'm just saving it for later when we want to find this second Jacobian, but I have it. I also have a symbolic variable for my theta. That's going to be my joint position. It's a 2 by 1 vector then I'm just declaring, hey, this is a real number. It's not a complex conjugate. Now, my home transformation matrix for this first center of mass, I'll call that T0 to 1. Again, let's think of like the spatial frame as 0, and this first center of mass, call that 1. So T0 to 1, that's a transformation matrix. That'll be identity, because in the home position, they're right on top of each other. Good, then I write down my screws that we just talked about, where S1 is normal and S2 is all zeros because I'm looking at my first center of mass. Then I have my code for the Jacobian that you see right here. And I extract out the 4th through 6th rows of that Jacobian. Maybe pause and think about why I did that. Well, it's because I'm looking for JV1. I want the linear component of the Jacobian to apply to this term right here. This is what I'm trying to evaluate. So I need JV1, so I just need the linear component, and that's the bottom 3 rows. And that's why I have the 4th through 6th rows right here, and that's going to give me JV1. All right, I found the first thing I needed. Now I can move on to my second center of mass. All right, so I'll be looking at this point right here. And this is, in this case, it's the robot's end effector. So this one's probably a bit more familiar with how you're looking at the Jacobian and the forward kinematics. So I'll go through the same process as before. I'll think about a transformation matrix from S to the second center of mass. I'll call that TS to 2. And in the home position, that's going to be L units off to the right. And we can just say the frames are lined up. Great. So here's my home transformation matrix for this second center of mass. My screw for S1 is the same as before. And now I also have a screw for S2 because I'm considering, the motion of this second joint will impact the position of this center of mass. And so I need to include it within my calculation. So I've got my home transformation matrix and my screws. I now can plug those into the code and try to find the Jacobian and the forward kinematics for this second center of mass. So here's my code. I start off the same as before. Now T02, that's my transformation matrix from S to the second one. It's identity and then L00, just what we defined. I've got the 2 screws I defined. And then I find T, my forward kinematics, and J2, my Jacobian for the second center of mass. Now I need to isolate the elements I'm looking for. For the rotation matrix, remember that's the top left component of my transformation matrix. And so that's what I find right here. I extract out the corresponding rotation matrix. And then for my Jacobian, I need to split that into the top 3 rows for my angular Jacobian and the bottom 3 rows for that linear component of the Jacobian. So I'll have J omega 2 and J V2 right here, the top 3 rows and the bottom 3 rows. And so I've got R2, J omega 2, and J V2, and I print them off right here. So you can follow along and see if you can get the same answers. Notice that this rotation, it's a pure rotation around the z-axis, which makes sense, right? Because as this joint moves, I'm just rotating on the z-axis. So again, kind of matches our intuition. All right, so once you've found all these terms, now you want to plug them back into your equation for the mass matrix. So I've got JV1, JV2, J omega 2, R2, and the other terms. I'm ready to plug those back in. Don't forget about the inertia matrix right here. I can plug those all back in and solve for my mass matrix. So here I am doing that multiplication. I just did it in MATLAB to make it a little bit easier. So I multiplied all these different terms that I'd found. I'm declaring some more symbolic variables. I'm saying, hey, M1 and M2, let's leave those as variables for now. This IZ, I'll declare that as another scalar variable. Those should all be real numbers. I spell out this the inertia matrix for the second link right here. I find my mass matrix, and I simplify it just to make it like a little bit easier to parse. And that's what you see down here. And I write that out also on this slide. So here's the mass matrix for our robot. Now, this mass matrix should be a symmetric, positive definite matrix. And we can see that it is symmetric. The off-diagonal elements are equivalent. And then I've got my elements along the diagonal right here. So I am getting a 2x2, a square matrix. And that makes sense. My robot's got 2 links, 2 joints, so it should be a 2x2 matrix. And here is my mass matrix. All right, so it's not easy, but we've gone through the process of finding the mass matrix for a robot arm. If you want to practice a little bit more, I encourage you to check out the practice set. In the first page, I've got the questions, and then the following pages have the solutions. You can find that in the discussion or the pinned comment. Once you've gone through that practice, we can move on to our next lecture. And here we're going to be thinking about the other 2 elements of our dynamics that we need to find. We'll be looking for the Coriolis matrix and the gravity vector. So I'll look forward to seeing you there.